like, share, subscribe.
Hey y'all, welcome back. So today we're just continuing practicing with these polynomial functions. So we're going to analyze and graph them. Let's just start at the beginning here. It says describe the end behavior of each function. So this is asking for you to describe whether or not the function is increasing or decreasing as it approaches either positive or negative infinity. So what we talked about in class was that we really only need to look at the very first term to determine the end behavior. And so we're really looking at whether or not the degree is even or odd, but also whether or not the leading coefficient is positive or negative. And that'll essentially give us our answer. If you want me to really break this down, go back to our notes video over sketching these polynomial functions. It's notes 2.1. And I go into a lot more detail on how I'm figuring this out. Okay, basically you're just looking at those two things I mentioned, and based on the degree of the leading term and the sign of the leading term, you can determine what the end behavior is. So this first one has an odd degree and a positive leading coefficient, so it's going to go down to the left and up to the right. So I'm going to write this just kind of in regular speak, down to the left and up to the right. So as x goes to the left, in other words, as x is approaching negative infinity, then we can say that the value of the function is going downwards, or it's approaching negative infinity. So the way we would write that in a little bit more technical speak here, if we're going to try to describe this using infinity notation, here's how you would write that. You would say something along the lines of as x approaches, and so this little arrow here is going to be approaches negative infinity. So basically what I'm saying is as x goes to the left, negative infinities to the left, positive infinities to the right. Let me just grab a little infinity symbol here. So as x approaches negative infinity, f of x, or the value of the function, the y value, since it's going down, we're saying it's going to approach negative infinity as well. Actually, I could probably just do this all in one little text box here. Okay. So that's kind of the better way of saying it. I am going to keep including these little short descriptions so that you can, if you're kind of confused about the notation, you can hopefully make sense of it. If we're going up to the right, then we want to say as x goes to positive infinity. So as x goes to the right, hopefully that's I'm pointing in the right direction that you can see. Is that right for you guys? Maybe that's left. I won't point because I think maybe the video's backwards or something. Okay, so anyway, as you go to the right, you are going to go to positive infinity because we're going up to the right. So as x approaches positive infinity, f of x also approaches positive infinity. So that's the description I'm looking for. Really, I want these descriptions involving infinities, I think, is a better way of saying it. But if we're just sort of discussing it, down to the left, up to the right, basically gets the same idea across, I think. So number 2, again, we're looking at that first term. So we've got an even degree with a positive leading coefficient here. So even degreed terms, we've got all kinds of colors here. I'm not sure what happened there with the colors. Make them all consistent. Yeah, that's weird. Anyway, when we have an even degree, both end behaviors are going to go the same direction, either up, up, or down, down. And if the leading coefficient's positive, that means we're going to be going up to the left and up to the right. So we're going to change this and say up to the left, up to the right. And so as x goes to either positive or negative infinity, f of x, or the value of the function, should be going up, so it's approaching infinity. Number 3 has an odd degree with a negative leading coefficient. So another odd degree, meaning the two end behaviors should be going opposite directions. And the fact that the leading coefficient is negative means that this is going to be reversed from number 1. And what I mean by that is we're actually going to be going up to the left and down to the right. Okay, so as x goes to negative infinity, f of x should be going up to positive infinity. And as x goes to positive infinity to the right, f of x should be going down. So that should be going down to negative infinity. Number 4 has a negative leading coefficient and an even degree. So we're going to have a function that has the same end behavior on both sides, but since the leading coefficient is negative, it's going to go down in both directions. It's going to go down to the left and down to the right. So whether or not x is going to positive or negative infinity, we're going to say that f of x is going to negative infinity. These are really the 4 cases. There's not really any other combinations here, right? Between the degree being even or odd and the leading coefficient being positive or negative, kind of knocked out all 4 potential answers you could have on these kinds of questions. So, these are just, one example of each, but hopefully you can kind of see the difference between all these problems here. So that's the end behavior. We do need to understand the end behavior in order to sketch the function. This one doesn't really ask us to sketch it, but we're getting there. The next section here says find the y-intercept of each function. So the y-intercept is going to be the point where the graph is crossing the y-axis. There's 2 ways you can kind of go about finding this. If it's not already in standard form, you're going to have to just plug in 0 everywhere where you see x. No matter what the graph is doing, if it's crossing the y-axis, it's going to have an x value of 0. So it's safe to just plug in 0 to x, evaluate the function, and that's going to be your y-intercept. Now, that being said, if your function is in standard form, like 5 and 6 are, notice how that if we just plug in 0 everywhere where we see x, so like here and here and here, these are all zeros, then all these terms are going to be 0, except for the negative 5. 0 cubed, 3 times 0, 9 times 0. Multiplying by 0 is just going to 0 everything out. So all the terms that have an x that we're substituting 0 into are just going to be 0, which means that the y-intercept is just going to be that constant term, because you're going to have 0, minus 0, minus 0, minus 5, right? The y-intercept here is going to be at 0, negative 5. And this is a little bit of a shortcut. You might remember slope-intercept form of linear equations, right? Y equals mx plus b. The b was your y-intercept, and that's because that was the constant of the function. If I were to plug in 0 for x of any linear function, you'd just be left with the y-intercept. So it is rather easy to find the y-intercept. Now, if you've got something else going on, maybe it's in factored form or the function just looks a little weird, if it's not in standard form like this, then you do want to just plug in 0 and then evaluate. Number 6 here, the y-intercept is going to be at negative 2. So we'll have 0, negative 2 here. All right, number 7 says write an equation in standard form for a cubic polynomial function. So cubic meaning it's degree 3. Okay, so that means we're going to have an x cubed. We should have 3 zeros. It says that has zeros negative 2, negative 3, and 4. So we're going to want to write the equation. I give a pretty big hint here. Almost shouldn't even give that hint, but just in case you're stuck, hopefully that kind of pushed you in the right direction. But basically, if you've got a 0 at x equals 5, that means that your function is going to have a factor of x minus 5. Because when you use the zero product property to split that up and you set x minus 5 equals 0, you're going to get x equals 5. Let me just kind of show you over to the side here, just as a quick example. So if x equals 5, that means that if I subtract 5 from both sides, I get x minus 5 equals 0. So that means that this right here has to be a factor. Okay. So whatever you see as far as whatever zeros they give you, you're going to just create a factor for each one. So like if the 0 is at negative 2, I'm going to have something at x minus negative 2, or in other words, x plus 2. So the sign in front of that number would be the opposite because of how you would solve it out. So x plus 2 would be a factor, x plus 3 would be a factor, and x minus 4. All these are factors, right? If I set each one of these equal to 0 and solve them individually, I would get negative 2, negative 3, and 4. Now, if this says, they could give me a little bit more information here. If they were to tell me what the y-intercept is, for instance, we might have to modify this equation by multiplying it by some constant, but they don't give us any more information. And we're just looking for a single cubic function that would have these zeros. There are infinitely many. You could really multiply this by whatever you want. It's still going to have those zeros. That would really just affect, the y-intercept and the maxima and minima and that sort of thing. Essentially, how stretched out the function is going to be away from the x-axis. So anyway, this is going to be our function. Let's go ahead and multiply this together. I'll just start by multiplying the first two. That's going to be x squared plus 3x plus 2x plus 6. I'm just foiling this out, multiplying, or using the distributive property if you like that a little better. Distributing the x to both of these terms, distributing the 2 to both of these terms, and these are all the terms I get. I have this nice little quadratic. I haven't combined any like terms yet, but I'm going to do that next. So yeah, I'm going to go ahead and combine the 2x plus 3x. It's going to be 5x. So I do need to multiply these together. This can be a little tricky, kind of hard to keep track of making sure you have all of the distributing going on. Essentially what you have to do is multiply each term in the first set of parentheses by each term in the second. You can do that by hand if you'd like. I like to use a little box method here, keep my work organized, make sure I hit everything that I need to. So here I'm multiplying a trinomial by a binomial, which is why I've got a 2 by 3 box here. So I'm just going to say x minus 4 down the side here. Make sure I multiply both of those terms by every term in the other polynomial, the x squared, the 5x, and the 6. Okay, so we're just going to multiply all this out. X squared times x is going to be x cubed. X times 5x is going to be 5x squared. X times 6 is going to be 6x. Negative 4 times x squared is going to be negative 4x squared. 5x times negative 4 is going to be negative 20x. Oh, grabbed the wrong thing there. Oops. Oh. And then finally, 6 times negative 4 is going to be negative 24. So now I'm going to combine my like terms. I've got x cubed. 5x squared minus 4x squared is going to be 1x squared. And then 6x minus 20x is going to be negative 14x, I believe. I think that's right. And then minus 24. So here's your polynomial. This one's guaranteed to have zeros in the correct places. There are other right answers, like I said before. If you multiply this whole function by some scalar, some constant, then you would get another function that would have the same zeros but is a little bit more stretched out. Or if you were to multiply by a fraction, I guess like 1/2, it would compress it a little bit more than it was. So anyway, I think this is probably the best answer for this question, or at least it's the one that takes the least amount of work. Let me put it that way. All right, let's do some graphing, yeah? All right, let's see here. Number 8. Okay, so this one's already in factored form. We don't need to worry about factoring. That's usually the first thing I suggest is to go ahead and factor it, but this one's already factored for you. Let's just make a note of everything that we see here. The first thing is, let's go ahead and find the roots. Okay, let's find the zeros. So if I set each one of these equal to 0 and solve them individually, I'm going to get x equals, here, I'll just write them as coordinates. Negative 2, 1, and 4. And I have no multiplicity here, so I'm not expecting any bounces. The graph should just pass through these x-intercepts. Maybe I'll just write them as x-intercepts. Okay, so those are the x-intercepts. We'll plot those in a bit. Let's now look at the y-intercept. Now, this is going to be a little trickier, right? Because this is in factored form, so we can't just look at the constant. We don't need to multiply all this out. So I think what maybe we should do is just find the first and the last terms, because those are really going to be the ones that give us information about what the graph looks like. The first term, the leading term, is going to tell us about the end behavior, and then the last term will tell us about the y-intercept. So for that first term, I'm just going to multiply all the first terms. So 3 times x times x times x is going to be 3x cubed, right? And then I'm not going to multiply everything else. We'll just say that there's a bunch of stuff going on in between here. And then the last term, if we were to multiply everything out, we just multiply these last terms. So 3 times 2 times -1 times -4. Let's see if I can do this. 3 times 2 is 6, times -1 is -6, times -4 would be a positive 24. So that constant term is going to be 24. You could also get this number by just plugging in zeros. 2 times -1 times -4 times 3. You end up at the same place. But I think just looking at it like this can kind of help, guide your thought process. So the y-intercept here is going to be at 0, positive 24. And just to abbreviate, I went through the infinity notation for the end behavior on 1 through 4. But if we're just sketching here, I'm just going to make a note of the end behavior, whether it's going up or down, because that's, the end. We can describe this a little bit easier, I think, a little bit more. How do I want to say? A little bit more understandable if we just use arrows, I think. So the end behavior here, since we have a positive leading coefficient with an odd degree, is going to be down to the left and up to the right. So we're going to say down, up, meaning go down to the left, up to the right. All right, so let's go ahead and plot everything here. It does not need to be to scale or anything, but I do want you to label all the key points here. Make sure they're on the right side of the axes and everything. So we'll just say 1 is right here. And I'll label these as soon as I get the points down. So we'll say 1 is right here, 4 is a little further out. Again, not to scale here, we're just kind of estimating where these points go. Here's -2, 0, -24. If it were to scale, it would be way higher, but we'll just put it there. All right, now I'm going to sketch this out. Oh, wait, let's go ahead and label. Yeah, I guess we should probably label. Here's -2. Here is 1, and here is 4. This is really the minimum amount of detail that you need to get a pretty decent sketch down. You don't need to scale out the axes or anything like that. Keep this simple. So yeah, 24 up here. So my graph is going down, up. So the first step in sketching this is going to be to just sketch the end behavior, right? So I'm going to go down here. I'm just going to kind of draw a little curve here, and then up to the right. I'm going to the outermost x-intercepts and drawing the end behavior from there, because I can't go back and cross the x-axis again, since these are my only places where I could potentially cross. Now, as far as the zeros go, we talked about how to know whether or not it's passing through versus bouncing off the x-axis. And since all these are just single roots, right, there's no repeated roots, none of these are squared or anything, so it's not going to bounce off the x-axis, it's just going to pass through. So I'm going to go up, hit this, come down, and this is just a rough sketch, but it's going to look something like this. One thing I'll note is that even though I drew this, and it kind of looks like the local maximum is right here, that's not necessarily true. Okay, we don't have the tools yet to figure out exactly where the maximum is, aside from just plugging in numbers, which I guess you could do if you wanted to improve the quality of your sketch. I'm not really worried about you finding where the local maximum is on a graph like this. That's something that you'll learn in calculus. And it's actually not even that hard, but it's not really going to be a focus of what we're doing now, and really don't want to get into derivatives and stuff. So it's okay to just kind of sketch. If you want it to come up and then pass down like that, that's fine. If you want it to hit the 24, go up a little further, and as long as you're hitting these points and have this general shape, I'm happy. So there's a sketch. Again, not really sure exactly where the maximum is. Or really the minimum for that matter. I mean, this might go down way further, but we don't know that. I'm not interested in making a table. This is good enough as far as I'm concerned. So yeah, let's look at number 9. This one is not in factored form, so we want to rewrite this in factored form. This one's going to be easy to find the end behavior and y-intercepts, but maybe the zeros not as much. So I'm going to factor out an x squared. It is the GCF of this, and it's going to leave me with x squared minus 4. which, yeah, just happens to be a difference of two squares, so we can factor that a little further. That'd be x plus 2 and x minus 2. There we go. Okay, so we're going to get a total of 4 roots. One of them is going to be repeated. Hopefully you can see which one. It's going to be this one at 0. So I do want to make a note that this one has a multiplicity of 2, because that's going to affect how we interact with the x-axis here. Let's write our x-intercepts here. X-intercepts, I've got 1 at 0. Right, if I set x squared equal to 0, I get plus or minus 0. But that does have a multiplicity of 2, so I'm going to make a note of that. The next one would be at negative 2 and positive 2. So we actually get plus or minus 2 here. So negative 2 and positive 2. The y-intercept, it initially was in standard form, so I don't need to go back and multiply anything out. I can just see that there's no constant there, right? Like if I plug in 0 into x, it's just going to be 0 minus 0, which is 0. And I should already kind of know that that's going to be my y-intercept anyway, because I already knew that it was going to pass through 0, 0 from finding the x-intercepts. So yeah, we get a y-intercept of 0. Last thing here is for the end behavior. Okay, this has an even degree with a positive leading coefficient, so that's going to go up, up. All right, so let's plot all these points here. We got one at 0, 0 right there at the origin. And that one does have a multiplicity of 2, so we're going to be bouncing off the x-axis when we start talking about that. And then we got one at negative 2 and positive 2. So really, those are the only two numbers I need to label here. The size of these dots, really, it's not really meant to mean anything. It's just me being a little sloppy here. Okay, so we'll start with the end behavior, up, up. So over here at negative 2, I'm going to go up. Same thing at positive 2. Okay, so the only x-intercept that's repeated is this 0, 0. So I'm going to pass through these, and then I'm going to bounce off the x-axis at 0 because of that multiplicity. Let's see if I can make that look a little smoother. Well, it's not perfect, but this is generally the shape of the graph here. And I've probably exaggerated how wide this opens up. It probably has a steeper slope, to be honest with you. But again, we're just trying to get a sketch down. I just want you to be able to have a general idea of what these graphs look like, not worry about all the details. Just as long as your intercepts are there and your end behavior is correct, and you're passing or bouncing correctly through the x-axis, you're going to be just fine. Okay, we've got a couple more here. Ugh, what happened here? So this should say 10. Okay, kind of a little embarrassing here. A little. I don't know what's going on here. There we go. Let me move that around. It's going to let me. All right, sorry for the little delay here, but I want to make sure this makes sense. Okay, problem number 10. Here's another one that is already factored. So we can go right ahead, just like what we did with number 8, and find the x-intercepts. In fact, just copy all this. We're just going to use this again. Obviously, we'll change the numbers and everything, but okay, so the first term is going to be negative x squared times x times x. So that's going to be a negative x to, there's 4 x's there, so x to the 4th. And then the last term is going to be, well, negative 1 times 2 would be negative 2 times negative 1 is going to be, let's see, negative 2, negative 1 is going to be positive 2. So my y-intercept right away is going to be 2. Okay, I'll come back for the end behavior. But the x-intercepts, this is already in standard form. We're going to have 1 at 0, 0, and that is squared, so that does have a multiplicity of 2. That's going to bounce. At the, oh, wait a minute, hold up. No, something's wrong here. this should, y-intercept's sorry, if I plug in 0 here, that's going to make all this 0. So yeah, the y-intercept is 0, and what really like threw up that red flag is the fact that I had an x-intercept of 0, so there couldn't be another y-intercept. So yeah, sorry, it should be 0 times 2 times negative 1, which is 0. Yeah, sometimes working these live, you make little errors here, but hopefully I can catch them all as we go. So yeah, so that's the x-intercept is going to be 0 and negative 2 and positive 1. Now the end behavior, since we have a even degree and a negative leading coefficient, that's going to go down, down. Down to the left, down to the right. So now we'll go ahead and plot this out. Got an x and a y-intercept at the origin. Got one at negative 2 and one at positive 1. Go ahead and label that. Negative 2, 0. 0 doesn't really need to be labeled as long as it's clear that you're on the axis. Here we go. Or clear that you're on the origin, I should say. Should be good. Okay, so the end behavior is down, down. We're going to go to the outermost x-intercept here and just kind of, these go down. And then 0 is the only one where we have a multiplicity of 2. So this is going to be kind of like the graph we just did, except flipped. So it's going to go up. Let's get up there. It's going to go up. It's going to bounce off the 0, and then it's going to come back down. And there's your sketch. Number 11 is also in factored form, so we're going to handle it kind of like we did number 10 here. Just copy and paste this work since it's going to be very similar. Here, our first term is going to be x squared times x. It's going to be x cubed. And then our last term is going to be negative 2 squared. Be careful there. Negative 2 times negative 2 is a positive 4. Okay, so you need to multiply that negative 2 twice, because really this is like x minus 2 times x minus 2. So negative 2 times negative 2 would be positive 4, times 3 is going to be positive 12. We're going to put our y-intercept at 12. Our x-intercepts, we have one at positive 2, which does have a multiplicity of 2 again. And then we've got one at negative 3. So we just have 3 x-intercepts here. Or I should say 3 roots, 2 distinct x-intercepts. And then for the end behavior, since we've got a positive leading coefficient and an odd degree, it's going to go down to the left, up to the right. Again, with that end behavior, if you're still struggling with that, go back to the notes, and I go into way more detail on how I determine what the end behavior is. But just a little quick thing here. It's just we're just looking at the leading coefficient and the leading degree. All right, so let's plot those points. Got one at 2, 0. That has a multiplicity of 2, so we're expecting a bounce there. And then one at negative 3. And then the y-intercept's going to be way up here at 12. Obviously not to scale here, or else 12 would be way higher. It's good enough, though. Going to label these, and let's go ahead and sketch our graph. It's going to go down, up, so I'm going to go to those outermost zeros, and I'm going to go down to the left, up to the right. Okay, I'm bouncing on 2, but not at negative 3, so I'm going to go up. I don't know, we talked about this earlier on number 8 when you have that y-intercept. Unless we investigate further, we don't know exactly where the maximum is. I mean, you could take an educated guess, but I'm not really going to look to see if this maximum is in the right place. That's something you'll learn next year, how to figure out where those maximum are. But this is just the general shape. So there you go. There's number 11. Okay, so that's enough graphing. This last section is just matching. If you are comfortable with the graphs we just did, this should be a piece of cake because the graphs are already done for you. Again, we're just looking at the end behaviors, the zeros, and so forth. Number 12 is just the parent cubic function. So it's going to go down to the left, up to the right, and have a triple 0 at 0, meaning that we are just going to kind of snake through, and we can see that their graph is going to be E here. So we'll put E there. For 13, this is going to be a cubic graph. with a a quartic graph with a y-intercept of 3. And this is not factored, okay? And I don't know that we'll be able to factor this. So finding these zeros can be a little tricky here if there are any zeros. But what we do know is that the end behavior is going to be up, up. So let's see if there's any choice as far as up, up. Yeah, so it could potentially be B, maybe F. Okay, so we'll come back to that. What was the y-intercept? Y-intercept is 3, so that's going to be what narrows it down for us here. And we see that this one has a y-intercept above 30, so it's got to be B. So using a little process of elimination here. 14 is going to be cubic with a positive leading coefficient, so it's going to be down, up, and it's going to have zeros at 0, -1, and 2. 0, -1, and 2 is going to be, looks like A. Down, up, you got 0, -1, and 2, and that's the only one that even looks remotely close, so that's got to be A. Number 15 is a cubic. Okay, it's going down, up. It's not factored, and it looks like, I don't even know if we will be able to factor it. Let's not worry about the factoring, but know that the y-intercept is 1. So it's down, up with a y-intercept of 1. And really the only other cubic function here that is going to be G, right? We've got down, up, y-intercept of 1. It looks like we do have a couple of irrational zeros here, so, but we're not going to worry about rational root theorem or anything like that today. So we could just narrow this down and say this is G. Number 16 is the parent quartic function, but flipped over the x-axis. It's going to have a multiplicity of 4, actually, for that 0 at 0. So we're expecting a bounce, and it's going to be down, down. The only one that's even close here is going to be C. Now we could use process of elimination to figure out 17. But if you were to solve this out, you would get zeros at plus or minus 2, plus or minus 3. Both of these are difference of 2 squares. So you could factor these, I guess, if you wanted to. X plus 2, x minus 2, x plus 3, x minus 3, if you're really looking to see where those zeros are going to be. So we're expecting 4 zeros. Yeah, with the y-intercept being, let's see, 4 and 9, that would be like 36, I guess, which kind of matches up with what we see on F, right? We got 2, -2, 3, -3, y-intercept up here close to 36, so it's got to be F. All right, well, I think that about wraps it up for this homework. Hopefully this helped you out. Thanks for watching, and y'all have a great day.